Hey everybody, my name is Max. I'm a research scientist from Yandex and High School of Economics. Today, I'm going to talk about one and a half of our recent papers on distributed training of large neural networks. The first of them is called Learning at Home towards crowdsourced training of large neural networks using decentralized mixture of experts. It's a recent newspaper, which was published like half a year ago. So it's publicly available. You can read it and ask me any questions if you have them. And of course, during my talk, if you have any questions right away, don't hesitate to interrupt me and ask them so that we can be on the same page all the time. Now, what's the paper about, basically? So, as some of you may know, recently in the past 2 or 3 years, we're reaching this era of scale in deep learning. I think somebody's trying to ask me. If not, all right then.
I think you just have not the best connection, and because of that, your video is a little bit low resolution.
Yeah, I was hearing some microphone noise from somebody else, but that's not a problem. Okay then.
Okay, yeah, that's a good suggestion that if you turn off the webcam, we'll probably see the slides better.
Oh, is it a problem with slides? Okay, then I'll turn the camera
much better.
off. Right. Now let's see and continue. We are reaching this era of scale where large-scale training of big neural networks becomes more and more popular. You can see this trend in computer vision, in natural language processing, and in other areas. For example, on the right, you can see this picture where you see the size of NLP models and how it increases through time. So basically, we have an exponential scale with larger models reaching 1 trillion of parameters. And we don't have it in this picture, but some papers by Google, for example, switch transformers, they reach even higher parameter counts. So given this trend, some research groups are already starting to study large language models and their implications. Basically, we see a certain sort of scaling loss of neural language models, which imply that if you train a larger model, you'll have higher sample efficiency, so you'll be able to achieve lower loss values in the same amount of training time, for example. And you'll also have interesting properties such as zero-shot inference. You can prepend a prefix which defines your end task, your downstream task, and the model will be able to perform according to this specification. This was demonstrated in GPT-3. Now, what does this mean for an average researcher, not from from top 3 or top 5 research groups all over the world? It means that some models might cost hundreds of thousands of dollars to train, or even more, due to these high GPU memory requirements. This also means that training of these models, for instance, GPT-3, may cost tens of millions of dollars in terms of compute only. As a result, it's hard to train such models for any average researcher, which does not, which isn't a member of these institutions, and to advance the field. For instance, if you're in a smaller academic group, or if you're a member of a company but a smaller one, it might be quite hard for you to reproduce and improve on these results. So for several millions of parameters, it might work, but for 100 billion parameters, it might be quite infeasible. Now, what can we do about this? So the solution which we proposed in our paper was to basically share the effort and to use idle resources of volunteers. This approach, called volunteer computing, has worked quite well in other sciences such as biology, high-energy physics, and so on. So let's do this in deep learning as well and see if that can be quite manageable. Now, there are some issues which are specific to this scenario of volunteer computing, which are quite important for when you are running deep learning on this infrastructure. I outlined 3 of them in this slide, but of course there are some probably less significant ones as well. The first of them is frequent node failures. Unlike your GPU cluster, you have some specific specifics related to the fact that some participants might decide to leave the collaboration, leave the overall computation experiment throughout this training run and turn off the PC, or maybe we can have some internet failures in some cities or even in some streets. So if you drop out of the network, it should be able to proceed with the training. Also, we have some issues related to communication over internet regarding specifically its speed, both bandwidth and latency. Because communication over internet, just as I demonstrated with my connection, is magnitude slower than on clusters. So yeah, we have this issue, and we also have to tackle it somehow. The third one is the problem of heterogeneous hardware, because we have different GPUs in our volunteer computers, we have different connection speeds, we need to take that into account. And our ideal case is that we're not slowed down by our slowest participant. So even if you have a GPU which is 2 or 3 generations past the state of the art of GPUs, you should still be able to meaningfully contribute to all of these computations. Right then. And it appears that all existing approaches for distributed deep learning fail to satisfy these constraints. For instance, if you're running data parallel training, you are limited to only small models, which fit a single worker. If you're trying to do a model parallel training like Megatron LM, GPipe, and so on, you are not limited in the size of your model to a single worker, but you are drastically less fault tolerant, because even a failure in one of the nodes of the entire pipeline can jeopardize all of the training, basically. And you also do not support any hot join capabilities for your network, because
I just want to basically point out that what we've been discussing before this talk is the first row. So that's exactly the model that we've been discussing.
Yeah, so the 4 above are well known in the distributed deep learning community. You can actually run the first one pretty easily. It's like touch distributed data parallel. Like if you've ever run distributed deep learning, odds are that you've used this one specifically. But all of them suffer from these issues I noted before. And our desired system is the one which can allow us to train large models with high throughput and fault tolerance, but it may be high latency. So we need to sacrifice something, and in our case, we sacrificed the latency for processing all requests. Now, the approach we propose in our paper is called learning at home. It's outlined by this figure. So basically, the approach is as follows. We have a large neural network, which is composed of several experts, of smaller subnetworks, basically. And for any specific training example, you only need a fraction of these experts. And all of them are located on different computers. So in order to proceed with your forward pass and backward pass as well, you just choose these experts, you locate them using a specific mechanism, which I'll elaborate on a little bit later. And then you just aggregate the results from all these experts. Now, for the specifics, we use a specialized layer, which we proposed in this paper, and it's called Decentralized Mixture of Experts. How does it work? If you're familiar with mixture of expert layers, it might be quite easy for you to understand. If not, don't be afraid, I'll explain everything. So imagine a single neural network layer. and make many independent copies of it. Like if you have a transformer layer, like both the attention and the fully connected parts, you can just replicate it several times. So you have several parallel layers of the same architecture, basically. And for this specific input, you only choose several of them. Like it's usually a small amount, 1 or 3 out of 10 or 20 or 1,000, depending on the number of your GPU memory. And then the distinction between usual mixture of experts and decentralized mixture of experts is that all these experts can be located on different computers with different hardware capabilities. So if you have a computer with low GPU memory, it can host one expert. If you have a large GPU memory enabled computer, it can host multiple of them. Then we locate the computers which host our chosen expert via something called a distributed hash table, or a DHT. This is basically a decentralized key value storage, which is maintained on all our network participants simultaneously. And it allows you to locate those peers over the network in a logarithmic number of requests. So it scales pretty well. It is designed to be fault tolerant and resilient to any basically members dropping out of your infrastructure. And if you've ever used something like BitTorrent or other peer-to-peer file sharing mechanisms, you've probably used that as a backend. Do you have any question or not? All right then.
Yeah, I'm not clear with how you actually pick experts. So you need to compute it, get an output. How do you pick which experts you need?
Yeah, for that one, we might go into a bit more detail here. Basically, this well, we have a set of experts, and we have some experts which we need to choose. This is done via something called a gating function. This is, for example, a linear layer on top of your input, which predicts the indices of the experts which you need to choose. And according to the distribution which you obtain as a result of this gating function, you pick, for instance, top K of those highest ranking experts. And the entire architecture, along with this gating function, is trained jointly. If we have time, I'll dive into a bit more details about how to scale this gating function to hundreds or thousands of experts. But for now, the approach is you simply predict those performances of experts for any given input, and you redirect your input to those higher ranking ones.
And do we then multiply the outputs by this predicted probability of an expert?
Yeah, that's true. In the original paper, which was proposed before switch transformers, we need to aggregate all those outputs with their weights. So if I'll actually discuss it in a bit more detail in this slide, but yeah, if we have these expert weights for any for all of our experts given the gating function, we take them into account for averaging both at the forward pass and the backward pass, in order for the entire network to be differentiable and trainable via gradient descent, right? So if we're using so we're basically encouraging our model to specialize on any specific inputs. Do I make myself clear? So we basically use this gating function for averaging, and we use its weights both for selecting the experts and for averaging, right?
Makes sense, right? So the result is the weighted sum of expert opinions, but you can actually throw out some of the last experts in this way.
Yeah, you're running a bit forward, but yeah, that's correct. If some of the experts aren't responding, for instance, or like due to timeouts or any network failures, yeah, then we just exclude them from this average computation.
No, but even if all experts are responding, you still exclude the least important ones, or don't you?
Yeah, that's also true. Like we can have 1,000 experts in our network and 1,000 classes in this getting function, but we only need to make network requests to a small fraction of them. This is this was originally the idea why we should use a mixture of expert layers here. So we have high capacity of a network on overall, and also we have but we still make a very small fraction of network requests, right? Given this idea of mixture of experts. We also have a question on something like Spark deep learning. It's not obvious to me, frankly, how to use and maintain a Spark cluster over a network of volunteer participants over the internet. Basically, I'm not aware of any projects which managed to achieve like this level of scale and this level of fault tolerance in something like Spark. If you have any projects which you can point me at, you can send it to the chat. But for me, it appears that this entire paradigm of Spark is slightly more suitable for clusters and so on. And in this scenario, we already have optimized algorithms and infrastructures like PyTorch distributed, like Megatron LAM, and so on. The issue is that when you're trying to scale it to something like volunteer collaborations, you can't do this, right? I hope I answered your question. Now, let us continue. Is an expert one of the layers of the neural network architecture? Actually, in our experiments, we replace all for this paper. We replace all of our layers instead, like the embeddings, with those mixtures of experts. So you imagine you have this sequential model and you execute layers one by one. You can replace all of your layers, excluding maybe the first one and the last one, by this mixtures of experts. So yeah, an expert is a component of one of the layers of the entire architecture. And each layer becomes, instead of one, like a convolutional layer, it becomes a mixture of convolutional or transformer layers.
Yeah, so I have a very specific answer to the question about Spark Deep Learning. So Spark Deep Learning is based on a library called Horovod. And there is an issue in Horovod about making it fault tolerant. And the issue is marked won't fix because it's too hard. So they're actually not solving the problems of like disconnecting nodes.
Yeah. I've heard of something like something called Horovod Elastic, which tries to like not achieve fault tolerance maybe, but to achieve like elasticity of computations and to support the scenario when people are trying to connect and disconnect frequently, like training on spot instances and so on. But it's also quite hard to make it running, and it still tries to achieve this synchronized state. So if your network is slow, at least for one of participants, the entire training run will slow to a well, it will basically halt, let's say. Now let's continue. So I've described the basic decentralized mixture of experts layers here, and how do we actually train over the internet. So this is illustrated in the slide from left to right. You choose those experts with a gating function, which I outlined before. You locate those workers using the DHT, and you send the inputs for the forward path to those experts. Some of them might not respond to you. For instance, they've gone offline, they are failing to respond in a given amount of time, so you can't wait for them. You are just, and then you just aggregate the outputs of the experts which have responded to your inputs. So basically, you average your outputs with the weights adjusted by the number of responses you've achieved. So you renormalize the sum basically. Then on the backward pass, you do the same thing. You send the inputs and the gradients for to those experts which have responded to you. Some of them might fail at that step, but still you can update the parameters of those experts which have responded, and then you get the gradient for the input and you continue with your backpropagation. So we can proceed in this manner and train a network basically for an indefinite amount of steps. Also, I should say that we counter network delays in this manner with something called asynchronous training. Basically, we aggregate the requests in batches on the expert side, and on the client side, on the trainer side, we are waiting for a given amount of time for all experts, and we wait for the first K to respond, and then drop all the others if they are too slow. So these improvements are basically what allows us to achieve high performance in the voluntary training setup and to achieve higher efficiency than other methods. Now, for the experiments in this particular paper, we only had the prototype runs, but we're currently working on something of significantly larger scale. I hope I'll have the time to discuss that. So basically, it appears that this asynchronous architecture and distributed mixture of experts allow us to train even with high latency in the asynchronous mode. It allows us to handle network lags and failures, and it scales to more than 10,000 DHC nodes, not like GPU nodes. So in experiments, we had several measurements. First of all, we achieve higher quality even on simple tasks when we're trying to train with a high number of experts instead of a single model which is trained asynchronously. This is related to the issue of gradient staleness, which arises when you're trying to apply the gradients for a different version of parameters. So some networks and some setups like simply using Hogwild or other parameter server approaches, they might suffer from this, but not mixtures of experts, because the subsets of experts used for all inputs are slightly different at each step. And on the bottom figure, you see that we actually managed to achieve higher training quality and higher validation perplexity when training a large language model on the Wikitext dataset when using this distributed mixture of experts. Now, for the conclusion, I'd like to say that in this paper, we tried to introduce this idea of decentralized deploying to the entire research community and show that it can be a viable alternative to expensive GPU clusters. If you want to learn more, you can read the landing page basically we've created at the link I show here, learning at home, GitHub.io. You can read also the paper and check out the code. Also, we're working on a framework for decentralized training. It's called HiveMind. It's in the stage of active development, but it's quite easy to use right now, and it's been tested. So you shouldn't run into too many issues when trying to run your own experiments. Also,
maybe some of our listeners can join you and submit pull requests.
Yeah, all contributions are welcome. Specifically, like we have a large community of students right now which do really good work with improving our repository and with adjusting it to other settings and scenarios. So yeah, we value all contributions and we are ready to help if you have any other questions. Okay then. Do we have any questions at that point? Because I also would like to introduce one more, an even more recent paper, but let me answer one question which I see in the chat. Fault tolerance is a difficult problem to tackle, but it would be a good starting point. So Spark deploying started with the execution different from generic Spark execution and is catered to distributed training in fault tolerance needs. Yeah, that might be what they say on paper, but yeah, I'm yet to hear whether it's a practical approach for this scenario which we're trying to achieve here. So we don't have any clusters, basically. We only have a number of volunteers or maybe a number of enthusiasts which have their own GPUs connected sparsely over the internet. So yeah, we have some issues even with orchestrating and with organizing everything in Spark. We can't have any centralized name nodes like they do in Spark, if I remember correctly. Okay, then I have another. Yeah, we have two questions. uh, do you think we'll be able to build some kind of a decentralized network of GPUs to train using the bubble of blockchain? Like users would be able to submit training jobs, and the network of GPUs can train the neural network. As the incentive, these miners get rewarded with something like Deepcoin. And it appears that the second question is also something like a blockchain model and cryptocurrency. Yeah, we've been approached on this like 2 times. Yeah, they're already here. They're among us. Yeah. So basically, we've been approached by these people 2 times before the seminar, and yeah, we haven't dived into this. Because we're still trying to solve all of these security issues, and we're trying to manage and train a large model, which wouldn't be which we'll be proud of and which will showcase this technology. And at that point, it might make sense to start converting it into something that people will have an incentive to use to run. But that's a bit of a future work. If you have any specific ideas on that, feel free to reach out. Let me just put my slide with the contacts here.
So
Yeah.
basically, you can fork HiveMind and turn it into a blockchain startup.
Yeah. If but we have a license, so cite us and cite the paper. Yeah, and we'll be we would be happy to help you with this blockchain from the HiveMind side. So you won't even need to like fork from HiveMind. You'll just be able to use it as a dependency. How to speed up scales with a number of nodes? Basically, given that this architecture is not bottlenecked by the number of nodes, the scaling is quite good. So basically, from this architecture, you can see that if you have like 100 experts or 1,000 experts, it does not affect your training performance in any meaningful way, because the only thing that you need to take care of here is the number of DHT requests, and you need to maintain this DHT network, and it scales pretty well, as shown in our experiments. There is another thing you need to take care of, which is the size of the gating function. But we managed to tackle this issue as well via separating this gating function into several sets of coordinates. Basically, it's like an IP. So like you have an IP address, and in our network, you have a tuple of identifiers. So if you're familiar with something like product key layers, you do the same thing, basically. You decide the priority of your experts basically based on the combination of those smaller identifiers. I can open the paper, or maybe if you need to ask, you can just hit me up on Telegram or on anything else. I'll show it to you in more detail. But basically, the question of frameworks. Right now, our implementation is tailored to PyTorch, but it's not significantly hard to like adapt it to something like TensorFlow, because all of the communication, all of the training runs, yeah, and also like on Telegram, we have this. On the side of the trainer, So you can use actually anything conceivable, because it's still converted to protobuf and serialized before sending it to via the network. And on server side, we have it in PyTorch, but it can be re-implemented in via anything you're interested in. Can I use it with PyTorch Lightning? Right now, we haven't tested it, but what you can do, like it's in principle, yes. We don't have any specific examples, and you're free to like try it out. And if you face any issues, file an issue or contact me. We'll see if what we can do. And right now, we're working on the project with which uses the Hugging Face Transformers library, and it tries and it trains a model using their training class, which is quite similar to the PyTorch Lightning library organization. So yeah, in principle, it can be done. Yeah, I'll just say before the end of my talk that also I'd like to, but it appears that we're running a bit out of time, with another paper.
So if you're worried, if you don't have time, that's fine. But our seminar, like, we have 40 more minutes planned. And if you want, you can go on.
Oh, yeah. Is there any techno-anarchist inspirations for the project? That's a very good question. There are many philosophical arguments which are behind this idea of training first and a cooperation independent network, and then there's one branch of thought, and another branch of thought is to have a planetary wide computer which can serve all these experts. So yeah. There are some philosophical arguments behind all of this. You can see the paper, like its introduction, that gives you the idea, the inspiration. Okay, then. So, yeah, I have actually a bit more time for the talk, so I'll discuss the paper as well. There's also a question of protection against crypto miners, because there have been news of cloud services being hijacked by hackers to mine crypto. I think, well, as of now, it's difficult for me to imagine how this can be hijacked by crypto miners, because, well, the infrastructure itself is running on some servers, and if those servers are running some code which is different from ours, it is mainly an issue of security on their side, I guess. If you're afraid of something like remote code execution, so some people can pretend that they're trying to train the network, and but they're mining crypto secretly. We're trying to implement specific features which will require the peers to actually verify their computation and to prove that they're doing useful work. This is something more of a work in progress, but in a month or so, we'll be able to show you the results of that. But basically, yeah, for given that we are at the application layer instead of like the infrastructure layer, we shouldn't have to worry about it that much. All right, then. Let me just
have a question on more of the machine learning side of that. You're using so the main hyperparameters there seems to be the number of experts in that mixture. And that sounds like something that's really hard to decide upon. Do you have any ideas, heuristics on how do you pick the number of number of experts?
Yeah, for the number of experts, you can actually, well, we support the mode in which you actually specify a large number of experts beforehand, and then it's basically the same thing. A very good metaphor for this is the network of IP addresses. It can be filled not entirely, and if some of the experts or computers do not respond, you just ignore them. So your network naturally adapts to those experts which are both present in this entire in your mesh of experts, in your swarm, and to those experts which are highly specialized to those given inputs. So basically, what you can do is to specify a very large number of experts beforehand, like to specify the size of this gating function output, and then just run the number of experts which you can allow, which you can afford. Then, if more experts join the entire network, it will naturally accommodate for them. Did I answer the question? So
Yeah, thank you.
the optimal hyperparameter is the highest number you can imagine, basically. Is there always one training machine in this infrastructure? The answer is no, and it's actually the one good thing about our project. You can run an independent number of both experts, of expert servers, and of trainers, because this architecture is asynchronous on both sides. So if you have many trainers, one expert can still process all of their requests, because it will aggregate them in batches and process them as they arrive. And then we can have, for one trainer, multiple experts, which multiple servers even, which host all of their experts. So no, you can run it with multiple trainer machines, and this entire architecture and our code, of course, is adapted to this scenario. So you have multiple trainers, multiple experts, and you utilize all of your resources to the highest extent. Yeah. It does sound cool. We are trying to currently train a large model, but let me just discuss one more paper, a half of a paper basically, to give you the idea of what we are capable of now. Basically, I've discussed that we can separate and distribute the computations of those experts of all intermediate layers across the network, right? But we also have one or two things which have to be synchronized somehow across the entire infrastructure, basically. Can you imagine what these two are? For instance, imagine that I'm trying to train something like GPT-2, GPT-3, GPT-4 with a very high number of parameters. So what parts of my network are still not distributed, across those experts? Do you have any ideas? So basically, I introduced one of them by introducing the mixture of experts layer.
I mean, there is the layer that decides on which expert to use.
Yeah, that's the gating function. I'm sorry on the correct pronunciation of your name, but the self-attention mechanism can also be sent to different experts. Like you can have an entire transformer layer delegated to some computer far away from you. The one thing which you need to synchronize in this setup is the gating function, is like this sublayer which decides which experts to choose for your inputs. And we need to synchronize it somehow, but as I said previously, it's quite hard to synchronize it via the mechanisms which we use regularly, like synchronize all across all of our network peers, right? So in a new paper, which is called Moshpit SGD, we proposed a new algorithm for decentralized averaging of parameters. So it's like decentralized data parallel training, right? It can be used for embeddings, for gating function, if you're running this mixture of experts training, or even on its own. So basically, in our experiments, we've shown that it's possible to run training for models like Albert Large, which is as very small in terms of number of parameters model, but still similar to BERT and competitive in terms of performance. And it appears that it's possible to use some unreliable instances, for instance, spot instances in the cloud, for these training runs. And you can even run it on Google Colab, given our current code. Unfortunately, I don't have the demonstration in this link, but if you're interested, I'll show you some examples in the repo. Basically, it allows us to train even when some peers can fail throughout training and if they are slow. Also, the paper and the code are available. Let me just show you a brief idea of this algorithm. For instance, imagine that you have multiple GPUs, multiple servers across your network, right? And you can separate them in a grid, like in a set of groups of roughly equal size. What you do then is that you run the averaging at each iteration only in these small groups. So you don't need the global synchronization. You just need to connect to a small subset of your peers. Like if you have 10,000 peers, you can have groups of size 10. So the communication they all use has to happen only in these smaller groups, right? Then at the next step, you separate those peers, but in a different set of groups. And what's cool is that you can do this in a decentralized manner. You don't need any central node which tells you which peers to collaborate with at this point. Then you run the averaging in a different group. And also, if some of the peers decide to drop out of the training, you're only losing the averaging results only in this small group. So basically, this is a simple way to average your parameters across the network, like it converges to the global average, without requiring the global synchronization. And that's how we managed to train this Albert large model across a wide array of cloud preemptible instances, across some local instances from our students, across even Google Colab instances, and so on. So it's a very cool idea on its own, but it also can be used to improve this mixture of experts training. Yeah, that's basically all for my talk. If you have any questions for this paper, also feel free to ask them. If not, I've shown you my contacts here. Oh, it's Twitter and email, but I'll also send the Telegram to the chat. Right, so if you have any questions, I can answer them right now.